So today we're going to be having a look at a recap of Unit 3, Topic 1, Bivariate Data Analysis, and this is our review. So this is to just make sure we're all on the same page. So there's 6 things I want to go through: explanatory response, coincidence and confounding variables, categorical data and 2A percentage tables, numerical data and scatter plots, direction form strength of scatter plots, Pearson's correlation coefficient R, and the coefficient of determination R squared, and how these both relate to a line of best fit. Alrighty, so let's get ourselves started. So the first thing we're going to talk about is variables. So for example, the first type of variables are explanatory variables and response variables. And the explanatory variable affects the response variable, or a better way of putting it would be that it explains the change in the response variable. So what does that mean? It means that as the explanatory variable changes, the response variable also changes. And this could be a simple example, if you climb, the higher the height in a tree, and then the chance of getting injured, right? As you go higher up in a tree, your chances of getting injured are also going to increase to a point, but they are going to increase. If you climb 10 meters into a tree and fall out, well, your chance of getting injured is going to go up as well. So this is directly causal thing. The explanatory variable affects the response variable. But there's a few other ways that variables can interact. This is a great example here. So number of people who drowned by falling into a pool, correlation with films Nicolas Cage appears in. And you can see you've got the 1999 data all the way up to the 2009 data. And you can see that they pretty well follow each other the entire time. Now, does that mean that Nicolas Cage appearing in films affects drownings, or that drownings affects Nicolas Cage? Well, no. There's probably a simpler answer, and that there's one of 2 things that are happening. Number 1 is coincidence, and the other thing is a confounding variable. Okay. So coincidence is exactly what it sounds like. It just happens to be the case that they follow each other, that there's no actual direct cause between the 2 variables, but it's just a coincidence. Confounding means that these 2 are related, the 2 variables are related, v1 and v2, but not to each other, not like in that above example, but instead there is a third cause that is affecting both, and we call that the confounding variable. So it's a variable that affects both of the variables we're interested in. So for example, if I go back to the Nicolas Cage for a second, well, the confounding variable could be that oh no, this is probably just coincidence. But there are options where sometimes it could be confounding. A classic example for confounding variables is the number of driver's licenses and number of hospitals in a town. And it's like, well, the number of hospitals doesn't affect the number of driver's licenses. And the real answer, which is affecting, is that there's a third variable that we're not talking about, which is that if both of these are increasing, or that both of these are following each other in some way, it's probably to do with the population of the town. Because the more people you have, the more driver's licenses you'd have, and the more people in town, you'd also expect there to be more hospitals, and vice versa. You'd expect the reverse to be true as well. So although these 2 appear to be explanatory variable and response variable, they have some sort of correlation. It's really a confounding variable which is affecting both of them. Alrighty, so that's enough about variables. Let's talk about categorical data. So let's talk about categorical data. So in this case, we're looking at categorical data. The first bit of categorical data is what we'd call male or female. It's our gender, and we would call this nominal data. Basically, it's a name, so there's no order to it. Whereas we have over on the top the age groups, in which we've got 0 to 5, 6 to 10, etc. And this would be called ordinal because you could order them together. But they're like categories. You can imagine they're like year 1, year 2, year 3, year 4, etc. In this case, we're just counting the people. So the first thing I want to do is let's just fill in the table. So strategy for this is you look for a row or a column in which there's exactly one gap. So in this case, the first row, the male row, has exactly one gap, which means that 6 plus something plus 14 plus 6 equals 30, or 30 minus 6 minus 14 minus 6 is going to be equal to the blank spot. And indeed it is. It's going to be equal to, it's going to be 14. Similarly, we can now start going down this column here, and we can see that we've got 6 plus something equals 12, well, 6 plus 6 equals 12. And now we can actually just start completing the table normally. So we can go 6 plus 25 plus 30 plus 19. It's going to be 75. And then we can start adding downwards. So we get 39, 44, 25. And we can add up both this way, and we should be getting the same total of 105. This should be 80, sorry. And so the total should be 120. This is why you check both the horizontal and the vertical, because it's a good way of double checking that everything's working. If it doesn't work both ways, then you've made a mistake. Alrighty. Now, this is pretty good, but imagine we wanted to, get a bit more information out of here. Currently, that's not much to read. Problem being that if I wanted to see if there was some kind of correlation between the age groups and males and females, well, the problem is that even here, I've got 6 and 6. So the numerical value is the same, but there's fewer men than there are women. Therefore, it's actually a higher percentage, that 6, than the 6 in the females, because there are 80 females. So in order to see whether there's causation or correlation, if we want to see if there's any association between the variables, well, we need to turn this into a two-way percentage table. And the way we do that is we choose which one we think is the explanatory variable and which one is the response variable. In this case, I believe that the gender is the thing that is explaining the ages. So explanatory and response. Once you know that, you do your percentage two-way table going down towards the direction of the explanatory variable. Alrighty. So now I've set up my two-way percentage table, and you can see I've put 100% down the opposite end of male and female. Why? Because male and female are my explanatory variable, so I always put them opposite that. Now to work out the rest of the data is quite easy. For males, for 0 to 5, there is 6 out of 30 times by 100, and that's going to give me the percentage. So 6 out of 30 times 100, and that gives me 20%. And we can go through and repeat this for each of the different numbers here. For, say, the females, instead, we're going to get 6 out of 80 times 100. And that's going to give us 7.5%. And now we can repeat that for each of the different numbers until we have finished. So for the next one, it would be 14 out of 30 times 100, and so on and so forth. I'll pause it and see how we go. And you can see how I've now got a percentage table. And the way I can now compare this is by comparing the percentages of the same thing. And in this case, you can see that there are significantly more men in the 0 to 5 age group per than there are females, because there's 20% for the men and there's 7.5% for the women. Conversely, you can see that for the 16 to 20-year-olds, that the women are more centered there. And you can also see for the men that they are quite heavily put into the middle category. Sorry, a mistake was made way earlier, and I didn't pick it up. Is that all of these numbers add together to actually add up to the special number known as 40, not the number 30. She's going to explain why all my percentages are wrong. Looking up that first percentage, it should be 6 out of 40 times 100, which is 15%. Which means this is going to be 15%, which means these are both going to be 35%. There we go, that looks a little bit better. And so you can see that the women are more dominant here and here. Oh, sorry, let me do it in red. So the women have a larger percentage in the older groups, whereas the men have a larger proportion in the lower ones. And so you can now actually compare these things. And so you could probably say something along the lines of that more men are aged from 0 to 10 per percentage than when compared with women who are more aged between 11 and 20. Alrighty, so that's an example of how to actually compare and see if there's any association between the different genders. An oldie but a goodie. So we're going to look at hours studied versus exams. So at the beginning, if we want to see whether there is any association between these two variables, the first thing to do is to work out which one is the explanatory and which one's the response. And in this case, the explanatory variable is going to be hours studied, and the response variable is going to be the exam score. And so we can now quickly draw up a scatter plot. Now, since the explanatory variable is hours studied, the explanatory variable is hours studied, that's going down on the bottom down here on the x-axis. So explanatory variable always goes on the x or the horizontal. Alrighty, so hours studied. And that's going to be 1, 2, 3, 4, 5, 6, 7, and 8. And the other one is going to be for the response variable, which is the exam score. Now we're assuming this exam score is out of 100. But you can see that most of the data isn't actually between 0 and 100. It's actually between 70 and 100. So this is the time where you might use one of these zigzags to specify the fact that we're one to skip a fewing to the number that we want to start at. So I'm going to start at 70, 75, 80, 85, 90, 95, 100. So that's not too bad. So I can go 80, 90, 100, and all of those data points will fit on this little graph. So now I can just do all of my points. So we're getting at 175, 160. Oh, sorry. No. Started too low. Let me fix this all up. That's why preparing your axes is very important to be careful, because sometimes you might just find yourself not fitting all of the numbers in that you need to fit in. So if you plan it out carefully, then you shouldn't have a problem. Alrighty, so now let's start putting in our points. So 175 goes here to 166. So you notice here, this wasn't allowed on a time series graph. We're only allowed to do this on a scatter plot, where you can have multiple points in the same vertical position or horizontal position. So we're going to get 274, 272, 485, 592, and 896. So we can look at this data and then start to see whether we think there's any sort of trend. Now there's a few things we can look for. The first thing is trend. Once again, this can either be positive, negative, or no correlation is the third option. No correlation would be flat. And it's certainly not flat in this case. It's quite positive looking. So for this one, it will be positive trend. The next thing we can look at is we can look at the form. Now the form can either be linear or non-linear. So in this case, you basically say, does it look curved or does it look like you could fit a straight line? In this case, I'd say it's pretty linear. There's a better test that you can do later on, which can confirm the form, but for the moment, eyesight's going to have to do. So it looks linear, so we're going to call it linear. And the last way we can do this is instead of the form, we can also talk about the strength. And once again, the strength, if it's no correlation, it's nothing, or it's strong, weak, oh, moderate or weak. Now, again, in this case, we've kind of just got to eyeball it. Same as the form thing, right? Does this look strong? Does it look moderate or does it look weak? I would say it looks moderate, but it's a guess. We don't know yet. How do we confirm? Well, I'm glad you asked me, because I'm about to tell you. We use what's called the correlation coefficient R. Now, R is a number between -1, 0, and 1. And it can take any value in this range. Now, depending on what the value of R is, it can actually tell us both the direction, and it can also tell us not the form, but it can tell us instead the strength. The main purpose we use it for is for telling the strength, but it does tell the direction as well. So if it's on the negative side, that means that it has negative direction. If it's on the positive side, it means that it has positive direction. If it's somewhere near 0, though, that's when we would say it has no correlation or no association. Okay, so these are kind of vague barriers, but if it's positive, it's positive. If it's negative, and if it's near 0, it's no correlation. So that's the sort of breakdown based on using the direction. So that's for the direction. For strength, let's do this in red. So for the strength is dependent on how close it is to certain things. So it is strong if it's between 0.75 and 1. It's moderate if it's between -0.25 and 0.75. And it's weak / no correlation when it gets near to 0. And same thing for above. And then moderate and then strong. So the strong region is between 0.75 and 1. The moderate region's between 0.25 and 0.75, and the weak region's between 0 and 0.25. Okay, so these are the different sort of regions we use to determine what the number actually means. How do we calculate it? That's probably a story for another day, but we use our calculator to do so. I will put up a separate video which shows you how to do that. But let's go through and have a look at what the R value for this data is by putting it into our calculator in the stats mode. In this case, we get R is equal to 0.94. We generally round it to 2 decimal places because it makes it easier to compare it using our little scale here. So on our scale, it is positive. Positive means it's positive, and 9.4, that's actually really strong. So 9.4 is up here, right? So it's positive, strong. And so when I guessed earlier that I thought it was moderate, well, that was actually a bad guess because I should have checked Pearson's correlation coefficient, R, and seen that it's actually, in fact, strong. So just so we're clear, positive and negative, and that you can look at visually, but things like form and strength can often be very tricky to work out without using a slightly more sophisticated tool. But just because it's strong has nothing to do with the form. So you can have a strong correlation and it's still being a little bit curved. You need to look at the data and see what you think, whether it's a straight line fits it or not. Alrighty, so we've talked about Pearson's correlation coefficient. Let's talk about its neighbor, which is the coefficient of determination, also known as R squared. Now, R squared is in fact equal to R squared. As in little r, we just calculate the coefficient correlation. Alternatively, you can think about R as being the positive square root of R. Okay? So whichever you want to think about it, so R squared is equal to R squared, which means that r is equal to the square root of r squared. Just so that we're clear, it's very rare that you need to convert between the two, but just so that it's in the back of your minds that r squared is literally r squared, even though we use an uppercase and a lowercase, they're in fact the same. And in this case, we've just got a slightly different scale. R squared does not go from -1 to 1, it goes from 0 to 1. And so we have slightly different cutoffs, but once again, it kind of tells us a little bit to do with the percentages, and it tells us a little bit to do with strength. And so we use similar cutoffs, but it depends on where you look them up. It's a little bit different, but essentially you can use quite similar sort of cutoffs as the other one. I tend to use slightly changed ones, but not too much. So it only tells us the strength. So 0.5 is still kind of the middle, and then we have 0.3 on the low side and 0.7 on the high side. Okay, and so in our previous example, the r squared value for this data is in fact, well, the coefficient of determination is 0.88, which is still within our strong category. Moderate, weak, and none. Okay, so it's slightly different. 0 to 0.3 is none, 0.3 to 0.5 is weak, 0.5 to 0.7 is moderate, and strong is 0.7 to 1. So it's slightly different than the other scale, but generally speaking, it'll be fairly clear which it's going to be, based on both the graph and on the number itself. The other way we can use r squared is to actually describe the relationship between the explanatory variable and the response variable. And we can do it like this. So the exam result is 88% changes in the exam result are 88% due to changes in the hours studied. Okay, so how can we use this more generically? Well, we can say this: changes in the response variable are, and then what we do is we take r squared and we multiply it by 100 to make it a percentage, due to changes in the explanatory variable. Okay, so this is kind of a sentence structure that we'll sometimes use when we're using the coefficient of determination. As we say, changes in the response are X percentage due to changes in the explanatory variable. And that sentence structure will come up every so often, and it's a useful one to know for knowing the coefficient of determination. Alrighty, so now should be in a pretty good position, ready to be able to fit lines of best fit and then go forward and be able to do some further linear regression. In particular, we're going to be looking at residual plots. Alrighty, I'll see you in the next one. Goodbye.